In this class, we are going to learn what is meant by this Kani's method and what are the advantages of this Kani's method over moment distribution method. Then, how to analyze an indeterminate beam or indeterminate frame with the help of this Kani's method. So that's the idea. So first of all, here, this Kani's method was developed in 1947 by Caspar Kani of East Germany. So here he is a person, Caspar Kani, in 1947 of East Germany. So here you can observe the names of the methods are being given according to their utility or according to the whatever the developed by whoever is the person. So with that name, the method is being given. So Caspar Kani in 1947, who is from East Germany, he has developed this Kani's method. So this is an iterative process or iterative method. So Kani's method is an iterative method. So iterative or iteration means, so the error will be minimized when you do number of times. In the similar way, in the moment distribution method, you have observed what we have done. The difference between the moments at a joint is distributed and it is balanced, then it is carried over to the carried moments are developed. So remember, in the moment distribution method, what we have done is the unbalanced moment is balanced. Unbalanced moment is nothing but just to see here. A beam is there like this. I'm just writing now in this. You have observed that we know that at a particular joint, the moments are to be equal. But you have observed that the value here it is 20, but here it is minus 35. So what we have done, this 20 minus 35, it is minus 15. So plus 15 is distributed to the, that is, it is balanced according to their distribution factors. So these distribution factors are, that is distribution factor is nothing but stiffness, relative stiffness of the member by relative stiffness of the joint. Relative stiffness of the member by relative stiffness of the joint. So from that we obtained the distribution factors. Distribution factors multiplied with the unbalanced moment, that is plus 15. Distribution factor into plus 15. So then this is balanced. After balanced, what you have done? You have done carryover moments. The carryover moments are written. Now, you can understand here, in the method of moment distribution method, the unbalanced moments are distributed. We are not going to the original fixed end moments or the moments. We are only balancing the unbalanced moments. But whereas, in this method, the joint moment is balanced. So that is the difference between moment distribution method and Kani's method. So in the Kani's method, the total joint moment is distributed. So we will write down the essential or the uniqueness of this Kani's method compared to moment distribution method. One by one points we will write down. So first of all, write down this point. It was developed by Caspar Kani in 1947 of East Germany. This method is an iterative method. So basically, this method is highly applicable in case of multi-storied frames. So Kani's method is can be effective at the analysis of multi-story frames compared to slope deflection method or moment distribution method. So wherever like multi-story frames are there. So in the previous analysis, what we have done is we considered only single-storied, single bay frames only. That means we considered the analysis of a frame like this, which is having one beam and two columns. That's it. But in real buildings, analysis of your buildings, you can see that there will be a series of like frames will be there. You can see this is double story. So when another frame is also there, this is three story. So like this, the number of frames will be there. So to analyze these frames, the analysis of slope deflection method or moment distribution method, it becomes very tedious. Why it becomes very tedious is in case of slope deflection method, you have to go with the. So just if I ask you, this frame is there. In this frame, then kinematic indeterminacy will be highly like larger. So if the kinematic indeterminacy is greater than 3, so what happens is you will get number of equations. Solving those number of equations in our calculator, you have only you can solve up to 3 unknowns. So the slope deflection method, if the number of unknowns are equal to 3 or less than 3, you can solve using your scientific calculator. If there are more than 3, yes, definitely you can solve it, but it takes a lot of time. Similarly, moment distribution method also, it takes a lot of time. So in case of this Kani's method, it will be very effective to analyze multi-storied frames compared to other methods. So till mid-80s, this method was effectively used to analyze multi-storied frames. But what happened was when some softwares, they have come to analyze the structures like StatPro, Struts, there are many other analytical softwares. So these analytical softwares, with the help of finite element analysis, they analyzed easily within a fraction of seconds. So it was vanished slowly. The use of this Kani's method was vanished. It was the charm started diminishing. So in the like from 1947 to 1980s, the people used to use this Kani's method, which is an iterative method. With the help of this method, they use it to analyze multi-story frames. Repeated distribution of moments at successive joints in beams and frames. This method is similar to Gauss Seidel iterative method. And is self-corrective. So that is the main advantage of this Kani's method. For example, while doing the iterative process, a slight error has occurred, like while adding or subtracting somewhere else, the assumed value is slightly wrong. But however, during the iterative process, it will be self-corrected, so that gives the accurate results. It does not require the solution of simultaneous equations. The solution of simultaneous equations, as in case of slope deflection method. So in case of slope deflection method, we use it to take the joint conditions. At joint conditions, you will get the number of equations regarding the unknowns. So the solving these number of equations, you will get the unknown displacements. So the unknown displacements will be substituted in the slope deflection equations to get the final end moments. MAB is equal to MFAB plus 2EA by L into 2 theta A plus theta B minus 3 delta by L, where delta is either sinking of the support or the sway. So in the case of this Kani's method, which is an iterative process, it doesn't require the solving number of series of equations. So that is one advantage of this Kani's method. So this Kani's method, here we will give a name that is called as a rotation contribution method. In case of moment distribution method, that is the moment is distributed. Here rotation is contributed. I will explain you while deriving the equation for this one. So in this, what happens is the main difference, write down. The main difference between Hardy cross. So the moment distribution was developed by Hardy cross. The Hardy cross moment distribution method and that of Kani's rotation contribution method. Is that in Kani's method, the total joint moment is distributed while in moment distribution method the unbalanced joint moments are unbalanced joint moments are distributed. The unbalanced joint moments are distributed. So here it is not a different method compared to slope deflection method and moment distribution method. It was developed with the help of slope deflection equations, which is another form of moment distribution method. So another point. Kani's method has been developed. Kani's method has been developed on the basis of slope deflection method, on the basis of slope deflection method with a different form of moment distribution method. With a different form of moment distribution method. Kani's method is advantageous due to its simplicity, speed, and accuracy. So this is about the salient features of Kani's method. The salient features of Kani's method, which was developed by Gaspar Kani in 1947, from a slope deflection method, and using the equations of slope deflection method, it is a different form of moment distribution method. It is not quite different from moment distribution, but a slight difference is there. The difference is nothing but in case of moment distribution method, the unbalanced moments are distributed, whereas in case of Kani's method, the total joint moment is distributed. So how the total joint moment is distributed, we will have a look on this. So now we will start analyzing a beam first of all. So we will develop the equations for this Kani's method. Keeps reading fundamental equations in Kani's method. Fundamental equations in Kani's method. So in the fundamental equations, we'll see first of all frames without sway as well as frames with sway. So in the analysis, I am starting with the frames without sway. So we already know that the frames, they will not sway when the loading is symmetrical as well as when the horizontal, like there is the displacement towards horizontal direction is restrained. So the frames don't sway in the following cases. The frames don't sway in the following cases. First one, when they are restrained at the end joints in rectilinear frames. So for example, see here, a frame is there like this. So here you can observe it is having a restraint along horizontal direction. So in this case, what happens is the provision of this support at this point, it will not, whatever the type of loading that is coming on the structure, whether you are having a UDL at this one or a point load at this one, that will not give any sway to the structure. So the horizontal restraint at the end joints in rectilinear frames, that will also does not create any sway. Second one is, the remaining things we already know. When the loading is symmetrical and there is no eccentricity, there is no horizontal loading, and there is no change in the moment of inertia of the section of the columns. So all these things doesn't give any sway in the structure. So to simplify all these things, we'll give in one sentence, symmetrical frames subjected to symmetrical loading. Symmetrical frames subjected to symmetrical loading. So symmetrical loading will also give non-space structures only. So in a simple matter, if you want to remember, when you take a mirror image, so if this is your structure like this or a frame like this, if you take the mirror image of the structure at the center, if whatever the image, if it is taken in the left side, if it is symmetrical to the right side, then you can simply say that the structure is non-space structure. Otherwise, the structure will undergo sway. So you have to analyze using sway analysis. Now we are considering non-sway analysis. So here I will consider a typical frame. For this typical frame, we'll start writing the equations. So just draw this frame. So here this is fixed here, this is also fixed here, and in this case it is fixed here, this is also fixed, and you can see that this is also fixed. So the rectilinear frame you can consider there. Here I am considering this is point A, B, C, and these 2 points are D and E. This is F and G. Now assume that due to this loading, here the clockwise rotation is positive if we consider. So the beam will rotate like this here at this point. This is a pinner joint, so the beam will rotate like this. So this will give a rotation which is theta A. And in the other direction, you can see that if you consider at B also there is clockwise rotation is existing. So it will go like this, which is in this way, which is theta B. If you draw the elastic curve of the beam, so the elastic curve of the beam will look like this. So at A and B, there are a clockwise rotations are happening. The clockwise rotations are theta A and theta B. Now, if I start writing the slope diffraction equations, MAB is equal to MFAB plus 2EI by L into 2 theta A plus theta B. So here we are considering non-sway conditions, so delta is 0. Minus 3 delta by L will be there, the delta will be considered as 0. Okay, so now this can be simplified in another way. MFAB plus 2 times of 2EI into theta A by L plus 2EI into theta B by L. I have just multiplied 2EI by L inside and I have written the equation in this fashion. Now here, this small 2EI by L into theta A, it will be replaced with rotational moments. So MAB is nothing but small MAB is 2EI into theta by L. Small MBA is 2EI into theta B by L. So for another simplicity, just to make it a small correction here, rather than writing capital A and capital B, I will write it as small ab, small ba. Now substitute these terms here. So MAB is equal to MFAB plus 2 small MAB plus MBA. So this is something like our equation, which is from slope deflection. We have assumed it as M small MAB is rotational moment. So you can write down this small MAB is nothing but rotational moment due to theta A and MBA rotational moment due to theta B. So what we have written is from the slope deflection equation, the slope deflection equations MAB is equal to MFAB plus 2EI by L into theta A. So instead of that, I have simply written as 2EI into theta A by L, which is considered as rotational moment due to A, that is due to theta A. Now, we know the joint condition. So according to joint condition, summation of moments at a joint is equal to 0. Sum of moments, sum of all moments meeting at a joint is equal to 0. So that means sigma m AB is equal to 0. So whatever the moments that are meeting at sigma m, summation of the moments at AB is equal to 0. So what is your sigma m AB value? Sigma m AB is nothing but this one only, right? So I can write down this sigma of MFAB plus 2 MAB plus MBA is equal to 0. So what we have done is here, summation of the moments according to the joint condition at a joint is equal to 0. So substituting, that is summation of the moments at a joint is equal to 0. Now you can write down this as sigma MFAB plus 2 times of sigma MAB plus sigma MBA is equal to 0. So here I will just take this rotational moment sigma MAB here. Sigma MAB is nothing but the remaining terms, they will come this side, sigma MFAB plus sigma MBA, which is multiplied with minus half. So sigma MAB is equal to minus half of sigma capital M FAB plus sigma small MBA. So I'm just waiting. You have to write down. That's fine. I will wait for another 1 to 2 seconds, 2 minutes. So please check it whether you have written these points or not. So what we have done, I'm just once again repeating. You can zoom wherever you would like to write. So here we have considered a non-sway frame where the support C doesn't create any sway in the structure. The presence of support C, it is not creating any sway in the structure. So if you consider A, B are two beam is a beam member which is between two nodes A and B. So here the clockwise direction moment is theta A. Similarly, theta B is also clockwise clockwise rotations. Now MAB is the final moment, which is nothing but summation of fixed moments plus rotational moments and displacement moments. MAB is equal to MFAB plus 2 EI by L into 2 theta A plus theta B, where I can simply write down as rotational moment, which is equal to 2 EI by L into theta A, 2 EI by L into theta B. Now the rotational moments are obtained at a particular joint. The total summation of the moments is equal to 0. So at a particular joint, if I consider for MAB, the summation of the moments at AB is equal to 0. Substituting MAB value here, and you will get rotational moment of AB or rotational moment of theta A, which is equal to minus 1 by 2 into sigma MAB plus sigma MBA. So this small sigma M into this small sigma into small MBA represents the rotational moment of theta B. Okay, now we will write another equation from another theorem. According to moment distribution method, if you remember, so what happens is we have balanced the unbalanced moment multiplying with distribution factor. So here distribution factor in case of moment distribution method is nothing but relative stiffness of the member to the relative stiffness of the joint. Okay, so here I can write down another point. So what I am writing is the balanced moment. I'm just writing. You don't write anything. Just listen. The balanced moment. For example, if I want to write down a balanced moment, so the balanced moment is nothing but distribution factor multiplied with unbalanced moment. So distribution factor is nothing but K by sigma K into unbalanced moment. So that unbalanced moment you will get it by adding the values. So write down from theorem 2 of moment distribution method. From theorem 2 of moment distribution method, from theorem 2 of method, MAB is equal to K by sigma K, KAB by sigma K into sigma MAB. So this is based upon your balanced moment only. So how you are balancing? So how you are balancing that? Go to your distribution method. So this is nothing but your distribution factor only, and this is nothing but your unbalanced moment only. So from this MAB is equal to KAB by sigma K, which is nothing but now in this one, I know MAB, I want individual rotational moment. MAB is nothing but KAB by sigma K into, in the above equation, you already know the value of sigma MAB. Substitute in this equation minus half of sigma MFAB plus sigma MBA. So this can be further simplified as the rotational moment MAB is equal to minus half of KAB by sigma K into sigma MFAB plus sigma MBA. So this is called as a rotational factor. This is called as a rotation factor. So you can replace rotation with rotation factor. MAB is equal to rotation factor of AB. Rotation factor of AB multiplied with sigma MFAB plus sigma M. So the rotation factor RF of AB is equal to minus half of KAB by sigma K. So KAB by sigma K is nothing but your stiffness of the member, relative stiffness of the member to the relative stiffness of the joint. So rotation factor at a joint, what is the maximum value of rotation factor, which is minus half? In case of distribution factor, which is equal to 1. In case of rotation factor at a joint is equal to minus half. Rotation factor at a joint is equal to minus half. whereas distribution factor at a joint is equal to 1. This FAB, this can be considered as a sum of restrained moment at joint A. Sum of restrained moment at joint A. Sigma M BA is equal to, okay, note on this. Analyze the given continuous beam with the help of Kani's method. So note on the beam. So this is the given beam. The moment of inertia of this is A, B, C, and D. Now we need to calculate the rotational factors. Here in the previous case we calculated distribution factors. Now in this case we need to calculate rotational factors. So when there is a fixity is there, rotational factors are equal to 0. UDL value is to be mentioned. Okay, so take this UDL value as 50 kilonewton per meter. This is the problem, so they are asking us to analyze with the help of Kani's method. You people know how to analyze with the help of moment distribution method. So for initially the distribution factors are used to be calculated. Now we have to calculate the rotational factors at each joint. At A and as well as at D, the rotational factors will become 0 as they are fixed supports. Now you need to calculate the rotational factors at B as well as at C. So keep citing rotational factors. So rotational factors at joint B I am calculating. At joint B, so the rotational factor for BA is equal to minus half of KBA by KBA plus KBC. So at joint B, there are two members that are meeting. One is BA and BC. So you can remember this is minus half of KBA. KBA is 1.5 I by 3. Remember here, the far end is fixed only, so that it is I by L only. This is I by L only. If it is a roller, it is which is something like hinged support or pinned support or roller support, then only it will be 3/4 of I by L, which is 2I by 4. So you can get this one. Can anyone of you tell me the value of this RFBA?
Minus 1 by 4, sir.
Minus 1 by 4. So RFBA is calculated. Now we need to calculate RFBC, which is minus half of KBA by, KBC. KBA plus KBC minus half of KBC is 2I by 4, 1.5 I by 3 plus 2I by 4. If you simplify, this will also become minus 1.4. So you can understand here RFBA plus RFBC is minus 1 by 2. So rotation factor at a joint, that will be equal to 1 by 2. That point we have to remember. Now similarly, now calculate at joint C also. At joint C we will calculate at joint C RFCB is equal to minus half of KCB by KCB plus KCD minus half of KCB. What is the value of KCB here? 2I by 4. KCB or KBC both are the same. 2I by 4 plus, here coming to KCD, the moment of inertia is I and the length is 4. Here you have to understand one thing, the far end D is fixed, hence there is no reduction in the relative stiffness of the member, which is, if the far end D is a hinge or roller support, then you might have get KCD as 3/4 of I by L. Most of you in the examination, you have done the mistake while calculating the relative stiffness of the members. Now what is this value?
Minus 1 by 3, sir.
Minus
1 by 3.
3. RFCB is minus 1 by 3. RFCD is minus half of KCD by KCB plus KCD minus 1 by 2 into, which is I by 4 by 2 I by 4 plus I by 4, and the value is minus 1 by 6. And coming to MFBC, which is UDL is 50. So the supports, they are simple supports, there is continuous support, but we assume it as fixed to calculate the fixed moments, minus WL square by 12 minus, which is 50 into the length is 4 square by 12. minus
6.64.
minus 66.67.
66.67 kilonewton meter. MFCB is plus WL square by 12, which is plus 50 into 4 square by 12 plus 66.67 kilonewton meter. And coming to MFCD minus WL by 8 minus 40 into 4 is a span into 8.
Minus 20.
MFDC is plus WL by 8 plus 40 into 4 by 8. So the fixed end moments are calculated, the rotational factors are calculated. Now we have to start analyzing our problem. So to start with this, now I have to draw my beam. So to draw the beam, here this is fixed end, I will draw this one like this only. This is my joint. For the joint, I will draw like this. And the last one is also fixed. So wherever your joints are there, give a symbol like this. Now this is your A, this is your B, C, D. Now first write down the fixed end moments. So first of all, write down the fixed end moments. At A, what is the fixed end moment here? So the fixed end moment at A is minus 35.55. This is minus 35.55. Whereas in this one, minus 17.78. So plus 17.78. Yes. Plus 17.78 minus 66.67. Minus 66.67 minus 20
Plus.
Now, after writing this, there is a significant
Plus
that,
66.67, sir.
yeah. Plus 66.67. Now, mention the rotational factors for the members at the joint. The rotational factor, if you consider here at this point, in this case, what is the rotational factor for BA? RF BA is minus 1 by 4. And this is also minus 1 by 4. Minus 1 by 4. Now coming to this, here for RFCB minus 1 by 3. This is minus 1 by 6. Now, the sum of restrained moment at joint B as well as at joint C. Sum of restrained moment is nothing but here the fixed end moments, these two are added together and they will be written here. So plus 17.78 minus 66.67. So the restrained moment is nothing but minus 66.67 plus 17.78, which is, tell me that value.
Minus
Minus
48.89.
Minus 48.89 kilonewton meter. The restrained moment at joint B. Similarly, restraint moment at the joint C plus 66.67 minus 20, which is plus 46.67. Plus 46.67. You may ask me what is the significance of this box and this box. For example, if you have a frame like this, if you have a frame like this, and if you have a frame like this, so there to write down these rotational factors, so these 2 points can be used. That's why that means it is separated like that. So only we have a beam elements. That's why the horizontally we have written the rotational factors. Okay, now we have to start our iterative process. So to start with the iterative process, we have to write down our rotational moments. The rotational moments are to be written. So rotational moments, if you write down the rotational moments, M, A, B, I will write down the rotational moments in this manner, in this here, 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 and here like this. We will write down the rotational moments. So as the rotational factor is the reason, as the supports are fixed at A and B, you can observe that MAB will become 0 initially. MAB is 0 only. The rotational moment here it is 0. Now I have to write down, so you can keep it as just give a space so that the values they will not be get confused, like iteration 1, iteration 1. So in this iteration 1, now M A B is equal to 0. Now MBA is equal to, so MBA is nothing but rotational factor of BA. So go to your formula, what we have derived. So what we have written, MAB is equal to RAB, that is rotational factor of AB, into sigma M FAB, that is at joint A. You have written this MAB for joint A. At joint A you have written, so AB plus sigma M BA. Now similarly we will write down for BA. MBA is equal to, that is rotational moment BA. Rotational moment BMBA is equal to RBA into sigma M F BA plus sigma M AB. Now in this one, if you observe, MAB is equal to RBA. What is the rotational factor? Minus 1/4 into, here sigma MFBA is nothing but the restrained moment at joint B. Restrained moment at joint B is nothing but your minus 48.89. Minus 48.89. So that is to be written minus 48.89. Initially, the rotational moments for every points are 0 only, so take it as 0 only, which is minus 1. Start writing for MBC. MBC is nothing but RBC into sigma M FBC plus sigma MBC. So RBC value, rotational factor. So what is the rotational factor here? Minus 1 by 4. Minus 1 by 4.
Sir, sigma MCB avudda sir.
Which one? Yeah, last one. Yeah. Right. Minus 1 by 4 into minus 48.89 plus initially we don't know the rotational moments and that's why it will be assumed as 0 only. In the next iteration they will be adjusted. So this will also become plus 12.25 kilonewton meter. So MBC is also obtained. Now the rotational moment at C we have to write down. So this is the rotational moments at B. Then we have written MBA as well as MBC. Now rotational moment at C. Rotational moment at C. MCB is equal to RCB into sigma M FCB plus sigma M BC. Sigma M BC. So in this one, now see this RBC. What is the RCB value? You got it as, just go to your diagram, then you can understand RCB. So this is your one. Rotational factor RCB is minus 1 by 3. So before that, let me write down the rotational factors, whatever we got, we'll substitute in this equation. MAB is 0, MBA is plus 12.25. This is also plus 12.25. And we are writing for MCB here. MCB is minus 1 by 3. So in this one, MBA is there, this one, plus 12.25. So 12.25 is to be substituted. So if you write down this MCB, the near summation will be with this as well as with this value. Just see here, I will, for the second iteration, you will understand what I am going to explain you. So RCB is minus 1 by 3 into, this is nothing but sigma MFCB. Sigma MFCB is nothing but restraint at the joint C. Whatever you have written this one, this is, you can simply write down sigma MFBA or sigma MFBC or sigma MFCB. We can write down this as, instead of writing this sigma MFCB, I can replace with MFC for simplicity, and this is, I can replace with this can be replaced with sigma, sorry, instead of writing everything. Why? Because we have already added and we have written the simplified value, which is MFB. MFB itself I can write down. Okay, so minus 1 by 3 into, what is this one? 46.67 plus 46.67 plus, now you have to write down MBC, sigma MBC, summation of the rotational moments. So the summation of the rotational moments is at C is nothing but, if we are writing the value at this one, when we are writing it here, the far ends are B as well as D. So the plus 12.25, here it is 0 only as it is fixed one. So that's why this will become 0 only. So we are writing here for this value. So to write with this, plus 12.25 plus 12.25 plus CD is equal to RCD into, instead of writing sigma MFCD, I can write it as MFC plus sigma MDC. For CD, here it will commit as MF sigma MDC. Now while writing here, RCD, the rotational factor for CD is minus 1/6 into MFC is plus 46.67 plus 46.67. Now you are writing the summation of the rotational moments at the far end for the C. Summation of rotation, see this one, sigma MCD, sigma MDC. It means that summation of the rotational moments for the far end. For the far ends, what are the far ends? Here when you are writing for C, the far ends are B as well as D. So this will be plus 12.25 plus 0. That is the far end. Plus 12.25 plus 0. Plus 12.25 plus 0. So what is this value? Minus 9.82. 82 kilonewton meter. So first iterative values are completed. So how many times we have to do the iteration? Iteration 1 is completed. With this you got your rotational moment values. So we have to continue this iteration until they are close, until the values are close. Now we will do iteration 2. So once write down. So at this step, those who are having a confusion, you can clarify all your things. So while writing the iterations 2, I will make you learn very easily. I am writing for M A B is equal to 0 only. Why it is 0? It is a fixed one where the rotation is not a load, so the rotational moment will become 0. Now, why I am writing is 0 is nothing but if you take theta A is 0 for fixed one. So corresponding rotational moment will also become 0. MBA I will write down. So MBA is what we are writing, RFBA into, this is we used to write as sigma MFBA. Instead of that I can write down MFB. That is restrained moment at B, which is written in the small box, plus sigma MAB. Now see this one. RFBA is minus 1/4 into MFB. We have written it as minus 48.89, which is also written in our box. Just go to the box. Minus 48.89. So just here I will write down what is the formula we have written. MBA is equal to RFBA into sigma MFBA, so plus sigma MAB. For BA this is AB. So summation of the rotational moments at AB for a particular joint is nothing but the far ends are to be considered. For B, the far ends are A as well as C. The far ends are A as well as C. So now, what are the rotational moments? Here, if you write down this, I am just writing here, RFBA is minus 1/4 into the summation of this sigma MFBA is nothing but MFBA plus MFBC. So these two are added and you have written minus 48.89 plus, you have to write down for this B, what are the far end rotational moments? What are the far end rotational moments? Just see here. I will change the color. See, this is far end rotational moment, MAB. Similarly, this is your far end rotational moment, minus 19.64. So 0 minus 19.64, that will be considered to calculate MBA. Minus 1 by 4 into, this is restrained moment. So when you are writing here, similarly when you are writing, only the change is with respect to your rotational factor. Whatever you are writing at a particular joint, within the brackets, that will be the same. So let me erase this. Why? Because it will disturb my, okay. So now what we are writing here, go back to our problem. We are writing here the rotational factor for BA minus 48.89 plus 0 minus 19.67 or 64. 19.64 minus 19.64. Now, what is the value here? 17.13 kilonewton meter. So plus 17.13. Immediately write down. AB is obviously 0. You need not write down once again. This is plus 17.73. Sorry, 13. 17.13. Now write down this next one. In this portion we have to write down. So for BC, MBC is equal to MBC is equal to, here the change is with respect to RFBC into MFB plus sigma MCB. So the same thing only, either sigma MAB and sigma MCB both are the same, minus 1 by 4 into minus 48.89 plus 0 minus 19.64, which is plus 17.13 kilonewton meter. So go back there, plus 17.13 will substitute plus 17.13. Now write down for MCB. To write down MCB, what I will write down? First of all, rotational factor minus 1 by 3 into plus 46.67 plus 46.67, which is that is the restrained moment at C, plus 46.67. Now in this, what we have to write down? For this, what are the far end moments? So far end, that is the far end rotational moments are plus 17.13 plus 17.13, it is 0. Other far end is 0 only. So which is plus 17.13 plus 0 plus 17.13. That means you are adjusting by the iterations. We are adjusting. So write down that. I will bring this one. Okay. So this is MCB is equal to RFCB into MFC plus sigma MBC minus 1 by 3 into MFC. MFC just now we have written, which is 46.67 plus 17.13 plus 0. What is the value? Similarly, MCD is equal to RFCD into MFC plus sigma M. BC or CD, DC, both are the same here. Sigma M DC, which is minus 1 by 6 into 46.67 plus 17.13 plus 0, which is minus 11 point,
3.
10.63.
10.63 kilonewton meter, minus 10.63 minus 21.26 minus 10.63. So I have to substitute those values here. Minus 21 point, what is the value?
26, sir.
Right. So second iteration is completed. So the values are whatever the iteration when you do. If I do the third iteration, I got second iteration value as plus 17.13. If I got the same value in the third iteration, then you can stop your iterative process. Until then, you have to do your iterations. Either you can show the steps in the examination, or otherwise you can directly write down here. So now for the third iteration, I will do directly here itself. So now, if I do the third iteration, now see this one, what happens? Obviously the first MAB is 0. You please keep side heading. Iteration 3. Iteration 3, that is better if you show, otherwise if you do, then that's also fine. So I have to write down for MBA. So simply what I will write down, MBA is nothing but RFBA, which is minus 1 by 4 into minus 48.89, which is in my table for minus 48.89. Now plus for this one, for at this point, what are the far ends? Don't say this is far end. No, for B, for this entire portion B, the far ends are A as well as C. So the far end is 0 minus 21.26. So for this, the far ends are this one as well as this. 0 minus 21.26. What is the value?
17.53.
So plus 17 point. Similarly, as the rotation factor is the same, you will also get here 17.53. The same thing only you will get, plus 17.53. Now go to here at this point. At joint C, you have to write down. At joint C, when you want to write down. So in this case, now what happens? See this one. I will write down MCB minus 1 by 3 into minus 1 by 3 into plus 46.67. So for this point, what are the far ends? Plus 17.53 plus 0 minus, what is the value?
21.4.
21.40. So this is minus 21.40. And MCD is nothing but, here the change is nothing but with respect to the rotational factor, minus 1 by 6, minus 1 by 6 into plus 46.67 plus 17.53 plus 0. What is the value?
Minus 10.7.
Minus 10.7. You can see the change in the rotational moments, they are becoming closure. So now if you do once again the iterative process, then you can minimize the error the fourth time. fourth time if you do the iterations. So I'm just erasing this part here. Here see, in case of MBA, for the fourth iteration I am writing. So the fourth iteration is minus 1 by 4 into minus 48.89 plus 0. The far end is minus 21.40. So this just change it as 21.40. And what is the value here?
Minus 17.57.
17.57.
17.57.
Yes, sir.
So this will be plus 17.57. This is also plus 17.57. Plus 17.57. Now coming to the next one, here this is, you have to, instead of 17.53, you have to substitute 17.57. So this will become minus 41. Just check this value.
41, sir.
Yes, minus 21.41. And this will become, you have to substitute 17.57. This will become minus 10.705.
706.
706. Okay. So that is 706. So which is, here the value is minus 21.41 and the value is minus 10.706. You can see the closure values and we can stop our iteration here. At fourth or fifth stage, you can stop your iterations and write down the rotational moments values. And write down the rotational moments values. I will write down here. The rotational moments I am writing here, which is MAB is 0, MBA is plus 17.57, MBC is plus 17.57. Add kilonewton meter. I'm just not writing that, but you have to add that also. MCB is minus 21.41. MCD is minus 10.706. MDC is 0. So these are your rotational moments. Don't take them as final moments. They are not the final moments. They are the rotational moments only. Now we have to calculate our final moments using slope deflection equations. If you remember, in the starting of the equations, developing the equations of Kani's method, we have written MAB is equal to MFAB plus 2MAB plus MBA. So MFAB value is, can anyone of you quickly tell me what is the value of MFAB?
35.55.
Minus 35 or
35.55.
plus 2 times of MAB. MAB is 0 plus MBA 17.57. So simplify this and tell me what is that value here. What is the value here?
Minus 17.9.
8, sir.
17.98.
98.
98.
And coming to MBA, MFBA plus MAB plus 2MBA. So which is plus 17.57 plus 0. What is the value of MFBA? Is it correct?
17.78.
17.78. Okay. Okay. 17.78 plus 0 plus 2 times of 17.57 plus what is the value?
52.92.
52.92, is it okay?
Yes, sir.
MFBC plus M2MBC plus MCB. So MFBC, what is the value of MFBC? Minus 66.67 plus 2 times of MBC 17.57 minus 21.41. What is the one?
Minus 52.94.
Yeah. 108 Sudarshan, you have raised your hand. Is there anything you would like to say? 108. Minus 50. Yes. Is there anything?
Minus 52.94, sir.
Now, those who have any doubts, I will solve another problem in the next class, and you will once again you can clarify. When you listen for the first time, you will definitely get confused with this substitution. As it is iterative process, you have to just understand from where we are writing all these values. That's it. MBC is written. You can check it your joint condition. MBA plus MBC. It is 0.02 only, which is you can make it as there is sigma MBA plus sigma MBC is equal to 0. Now MBC is written. Now MCB, MFCB plus 2MCB plus MBC. 66.67 plus 2 times of minus 21.41 plus 17.57 plus
41.42.
41 point
42, sir.
MCD, MFCD plus 2MCD plus MDC. So MFDC is minus 20 plus 2 times of MCD minus 10.706 plus 0. So which is minus 41 point
412.
412.
kilometer. Once again, you can check it, the joint condition MCB plus MCD, it is 0. And MDC, MFDC plus MCD plus 2MDC plus 20 plus 10 minus of 10.706 plus 2 times of 0, which is plus, what is the value? 9.
9, sir.
9.294.
Kilonewton meter. So these are your final end moments. So try to do the problem as our previous problem only.